Alrighty, ladies and gentlemen, attempt number 3 to get these videos all worked out and with audio this time, hopefully. Welcome to the 3 videos that you are going to be watching this week as part of your continuing ed in geometry. I'll go ahead and get class started for you with jazz hands 1, 2, 3. Happy whatever day it is for you. Again, I hope that things are going all right for you and you're transitioning into digital education without too much angst. With that said, we're going to kind of jump in today and start talking about our new unit, which focuses on area of triangles, or area in general. And today's lesson will focus on area of triangles and quadrilaterals, which are many of the concepts that you've been introduced to in the past. Now, if you would like a digital copy of this notes packet, it is in Canvas in the COVID-19 Continuing Education folder in the Files section, and in week 1. There's a digital copy in PDF form you could download and print off if you would like. But we'll go ahead and get started, and hopefully this will be valuable for you. So as we jump into area, though, there is one thing that you need to be aware of, which is that a lot of area style problems are going to relate back to the 30, 60, 90, and 45, 45, 90, and special right rules and trigonometry that we learned, because triangles form the foundation of a lot of the area formulas that we later will go and calculate. So with that to say, let's make sure to review some of the essential formulas before we move on further in the lesson. So to kind of help us go back and think through our process, one of the first special right triangle rules that we learned was the 30, 60, 90. And a 30, 60, 90 triangle, if you remember, has a short leg, a long leg, and a hypotenuse. Now, to move between these different sides, there was some scale factor that we had to learn. For example, to move between the short leg and the hypotenuse, the factor of change was a factor of 2. And if we're going from the short leg to the long leg, we're going to multiply by 2, because we're going from small to big. If we're going to go from the short leg to the long leg, again, we're going to multiply by the factor of change, which in this case is square root of 3. We also learned about 45, 45, 90 triangles, which just so happened to be even more convenient to work with because the legs ended up being the exact same length. And the hypotenuse is longer than the legs, but it has a factor of change that remains the same in a 45, 45, 90, which is to say to go from the leg to the hypotenuse, we multiply by square root of 2. Last but not least, we talked about Pythagorean triples. These were 3 integers, so 3 numbers without decimal, that could be used to form the sides of a right triangle. And this was all tied to a famous theorem discovered called a squared plus b squared is c squared, known as the Pythagorean theorem, which allows us to know that in any right triangle, the hypotenuse and the legs are related by that formula. Okay. Last but not least, the other things to review are 3 trig ratios: sine, cosine, and tangent. These ratios allowed us to relate the sides of right triangles as well as to solve for unknown measurements, either angles or sides. Sine compared the opposite to the hypotenuse. Cosine compared the adjacent to the hypotenuse. And tangent compared the opposite to the adjacent. With these 6 tools, we are now set up and ready to start working with basic area principles. And these tools will come into play to help us find unknown measurements along the way. Now, before we jump into actual problems using these tools and actually looking at some areas, we probably want to make sure our definitions are very clear. A reminder that while you can probably think of area in your mind, a helpful thing to know is also how to describe it. Area is the 2-dimensional space enclosed by a figure. In other words, it's the stuff inside a closed figure. How much stuff is in it? This is similarly related to the idea of perimeter, which is not the 2D space, it's the one-dimensional space that is, or I'll say one-dimensional space / length around a figure. So it's as if we were to try to trace our finger around the outer edge. Now, those of you that have worked with circles before know that there is a special name for the perimeter of a circle, which is called circumference. This is, whenever you see circumference, just think, oh, they're talking about the perimeter of the circle. We call it circumference more than perimeter, because perimeter, a lot of times, we talk about with things that have flat edges, flat sides, like a triangle has straight segment sides, whereas a circle is all curves. But the general idea of it is the same. Just want to make sure you have that terminology. Now, back when you were introduced to area, you were very likely introduced to the most basic of areas, which is the area of a rectangle, base times height. This is based on the idea that area looks at the length and width of a particular set of a particular enclosed figure. And it breaks that figure into unit blocks. So notice as I kind of tile this whole space here, and maybe I'll try to be a little bit better spaced out. Didn't do a great job, but there's my best attempt. This broke this figure into 4 units of height. And if I were to carry those units across, I would create strips. And then if I also figured out how wide I had broken this into, 10, 11, 12, 13, I could take those strips and interlace them. This creates for me unit squares, and this is the core foundation of area, is how many unit squares are made when we make strips out of both the length and the width, or the base and the height. And it just so happens that the number of individual unit blocks is the product of our length and our width. Now, sometimes the length and width are the same size, giving us a square, which of course means we can find the length of one of the sides squared to find the area's squares, which is great. But the other one that's really handy that you might not be as familiar with is the area of a parallelogram. It just so happens that a parallelogram, because of its properties, is really just like a slanted rectangle. And in fact, if we draw in the height, as you can see here, directly perpendicular to the base of the parallelogram, what ends up happening is we divide that figure into 2 parts. And in removing the part on one side, that triangle, we can reattach it on the other side in order to create a perfect rectangle. And what you'll notice is the base of that particular figure doesn't change. We just cut off the slanted bit, and the height doesn't change. So really, we're just rearranging the figure in order to get a rectangle, which means the area of a parallelogram is also just base times height. Now, this can get slightly more involved, and where it does is when we start talking about situations where we want to find the area and or perimeter, but we don't have all the measurements we need. And this is where our tools from up above, our special right rules, our Pythagorean theorem, and our trig ratios can be helpful. Because notice in this situation, we've been asked to find the area of the parallelogram and its perimeter. Well, notice that by drawing in the height here, this particular mathematician has discovered that the space to the left of that height is a 30, 60, 90 triangle. And the advantage of that is of course, they can use their 30, 60, 90 rules in order to find unknown measurements that they need to find the area and perimeter. Now, the first measurement they might want to find is how much of this particular figure is to the left, how much of this base is to the left of that height. So they want to go from the hypotenuse to the short leg in a 30, 60, 90 triangle. And it just so happens that the factor of change is a factor of 2. Well, we're going from the hypotenuse to the short leg, so we need to divide. So when I take 6 divided by 2, I get 3. Then I can go to the long leg, and again, I'm going from something short to something longer. So I'm going to be multiplying, and the factor of change between the short leg and long leg is square root of 3. This is the height of both the triangle and the parallelogram. So now I'm in a good place because I know that a parallelogram has opposite sides congruent. So if this is 6, this is 6. This whole base is 15, so this whole base is 15. And now I can answer both of the questions I was asked. First, perimeter. Well, perimeter is just a sum of all the sides, as if we were tracing it around the outside. So the perimeter of my figure is 6 plus 15 plus 6 plus 15. The perimeter is just 42 units. The area, on the other hand, which of course is, again, all the space enclosed by this figure, is going to be the height, which we can see here we were able to calculate, times the base that it's perpendicular to. Well, that means our area is going to be 45 root 3 units squared. Perfect. And that's the area and perimeter of our parallelogram. So again, our right triangle rules became a tool to find the relevant measurements we needed to find area and perimeter. Okay. Now the next area ratio you were probably introduced to back when the idea of area was introduced to you was that of a triangle. And the reason for this is a triangle, it just so happens, always ends up being half of a rectangle. And by duplicating either the whole triangle or, in the example on the left, the parts of the triangle, you can often mirror or rotate those in order to create a full rectangle. What that means is that the parts of the triangle make up exactly half the area parts of the rectangle, thus giving us 1/2 base times height as a formula. Now, again, sometimes we'll have to do additional work before we can find our area and perimeter. Again, you'll notice here this is a right triangle, so I can use a handful of tools available to me. Now, it's not a special right triangle, so I can't do 30, 60, 90, or 45, 45, 90 rules. I don't know the angles. I could try using trig, but again, trig is going to require me to find the angles first, which is maybe a little more work than I want to do. But I could also do Pythagorean theorem in order to find the length of this third side, because this is a right triangle. When I do Pythagorean theorem, what I'll find is that the answer I end up getting is that x is 40. Now that I have that, I can answer both of these questions with ease. Again, the perimeter is that one-dimensional measurement, as if I were to walk around the entire outside. It's 30 units and 40 and 50 to give me 120 units. And the area, which is the space enclosed, I need to find a base and a perpendicular height. Well, here's a base of 40 and a perpendicular height of 30. And then the area of a triangle is base times height divided by 2. So the area is 30 times 40 divided by 2, which is 600 units squared. Now, as a pro tip, you might at some point work with a triangle that is not a right triangle, which seems very difficult and problematic, and it can be. But one trick will really help you with this, and it's to realize that even if your triangle is not a right triangle, you can often draw in a measurement of the height, draw in an altitude. And often in these triangles, you will know the angle measures that will be given to you. Now, in an equilateral triangle, I know that they're all 60 degrees. But when I draw in that height, I split it into a 30, 60, 90. Which you'll notice, once I do that, again, this is 2.5 and this is 2.5. Once I do this, I now have a 30, 60, 90 triangle. I can use my relationships to find the height and compare that to my base of 5. So again, we can even break up big triangles into smaller triangles in order to help us find unknown measurements. So again, to summarize, in a non-right triangle, draw in a height, find its measure, using special right rules and or trig, then calculate area. Great. Now, the last basic area formula you probably learned when you were introduced to area is the area of a circle. And this is actually kind of an interesting thing because it involves and introduced the idea of pi. Pi is an irrational number, but it's a number that describes the relationship between the diameter of a circle, which is the distance straight across, and the circumference, which is the distance around the curve. What's interesting is that the circumference is always pi times bigger. It is always 3.14 blah, blah, blah times bigger to walk around a circle than to walk across it for every circle, which is pretty wild. That's how we get this nice formula, circumference is pi times diameter. We also have another formula involving pi, which relates the area of a circle to the square of the radius times, again, pi, which is pretty cool. Now, to talk about a relevant problem for those of you trapped inside during COVID-19, here's the thing. I see a lot of deals going around to order pizza these days. And in fact, a friend of mine just recently ordered 2 8-inch pizzas instead of 1 12-inch pizza for the same price. Here's what's interesting about that. If you actually do the math, it turns out that it's actually more pizza to buy 1 12-inch pizza than 2 8-inch. Not only because you save space on the crust, but because the pizza itself is that much bigger. And again, the reason for that is that the area of a pizza of a circle is dependent on the square of the radius. So any increase in the radius increases the size by an even larger degree. So let's look at this problem. Again, we've got a 12-inch pizza in diameter, which means its radius from the center, to the edge, that is going to be 6 inches. And we have a 10-inch pizza, which again, the radius to the edge of that would be 5 inches. Great. So if somebody asked you, what's the better deal for pizza, or how much better of a deal is it? What we could do is we could calculate these formulas. The area of these is pi times the radius squared, which means this has 36 pi inches squared of pizza. This is our 12-inch diameter. Our 10-inch diameter has 25 pi inches squared. Now, this may not seem to be a considerable difference, but what it means is that the 12-inch pizza has almost 50% more pizza than the 10-inch pizza, which is pretty wild. So keep that in mind when you order your pizza. Now, this is the first video, and this is our conclusion of it. Really, it's an overview of the 3 most important area formulas that form a foundation for our area in geometry. The rectangle/parallelogram, which deals with the base times height formula, the very foundation and definition of area. The area of a triangle, which is half that of the parallelogram that encloses it. And the area of a circle, which is related by this factor of pi. As long as you as you get those processes and formulas down, you're going to be good to go for this first lesson, and you might give the worksheet a shot before you move on to the next one. Thanks so much for your time.